In this video, we will discuss how to draw the correct geometry for an E2 product. And we will also discuss how to draw the mechanism for a reaction with multiple E2 products. Let's begin by discussing this issue of molecular geometry. Please pause the video and answer these questions. Now here are the answers. A carbon with 4 attached atoms has tetrahedral geometry. A carbon with 3 attached atoms and no lone pairs has trigonal planar geometry. I'm just briefly reviewing facts that you really should already have learned in your chemistry and OChem courses. How would you answer these questions? Well, here's the answer. Geometry for a tetrahedral atom is indicated by 2 solid bonds, a wedge and a dash. On the other hand, geometry for a trigonal planar atom is indicated by bonds that are all indicated by solid lines. Next question. What is the geometry of an alkene carbon? I hope you came up with an answer. Here's an answer. Well, here's an example of an alkene. This was the product from the last question that we worked on. And do you see that this alkene carbon has 3 attached atoms and no lone pairs? 3 attached atoms if you count the 2 hidden hydrogens. 2 hidden hydrogens in carbon 2, that's 3 attached atoms, and there's no lone pairs. Carbon 2, the other alkene carbon, also has 3 attached atoms and no lone pairs. The 3 attached atoms are carbon 1, carbon 3, and a hidden hydrogen. We can figure out the number of hidden hydrogens by remembering that each of these neutral carbons should have 4 bonds total. Okay, so we would imagine that, that those alkene carbons have 3 attached atoms and no lone pairs, so they should all be trigonal planar. So that's the answer to this question. An alkene carbon is trigonal planar. So let's go ahead and make sure we're drawing that geometry correctly. How would you draw the geometry around carbon 1 if you were also going to show the hidden hydrogens? Here's the answer. So here I've shown the 2 hidden hydrogens. Notice now that we have 4 bonds total around this neutral carbon. Notice that all of the bonds are drawn with solid lines. For trigonal planar, all the bonds are drawn with solid lines. It would be a mistake to put one of these hydrogens on a wedge or a dash. Because what does planar mean? Planar means that all 3 attached atoms are in the same plane. So generally speaking, for a trigonal planar atom, all 3 attached atoms will be in the plane of the page. Here, carbon 2 is in the plane of the page. And we also want to put both hydrogens in the plane of the page to show that all 3 are in the plane of the page. That makes this trigonal planar. So try drawing the geometry around carbon 2. Well, carbon 2 has 1 hidden hydrogen, and again it should be drawn on a solid line so that it's in the same plane of the page as carbon 1 and carbon 3. It would be a mistake to draw this hidden hydrogen on a wedge or a dash. So the important point that I'm making is that usually we draw all the bonds around alkene carbons with solid lines. My point is that when you use an E2 reaction to make an alkene, you should usually draw all the bonds around the alkene carbons with solid lines, not with wedges and dashes. Alkene carbons are trigonal planar. Their bonds are usually drawn with all solid lines. What's the geometry at carbon 3? What's the geometry at carbon 3? Well, carbon 3 has 4 attached atoms, so the true geometry for carbon 3 is tetrahedral. Now notice that we have not drawn that geometry accurately here. If we were going to accurately draw tetrahedral geometry, we'd have to use a wedge and a dash. We didn't bother to draw the geometry accurately here because this is not a stereocenter. And when an atom is not a stereocenter, we usually don't care about the geometry that much. But just for practice, why don't you redraw the geometry at carbon 3 correctly? Show the geometry at carbon 3 correctly. Well, here's a more accurate way to show the tetrahedral geometry at carbon 3. Now we're accurately showing this tetrahedral geometry with two solid bonds, a wedge, and a dash. Two solid bonds, a wedge, and a dash. That's the accurate way to draw tetrahedral geometry. But again, that doesn't mean that this picture would be marked wrong. This picture wouldn't be marked wrong because when a tetrahedral atom is not a stereocenter, we don't usually care about drawing the geometry accurately. So this would be considered a correct answer, even though the geometry is not drawn accurately here, because since carbon 3 is not a stereocenter, we don't really care about its geometry. But if we wanted to draw the geometry accurately at carbon 3, this would be the way to draw it. Two solid lines, a wedge, and a dash. If a tetrahedral atom is a stereocenter, then usually it is important to draw its geometry accurately with two solid bonds, a wedge, and a dash. Well, obviously the reason we're going over these geometry facts is because they can be useful for E2 problems, and we'll illustrate that in the next problem. One more comment about geometry. I should have mentioned that, do you know what the bond angle is for a trigonal planar atom? A trigonal planar atom has a bond angle of 120 degrees. That means that this bond angle should be roughly equal to this bond angle, which is roughly equal to this bond angle. And this bond angle should be roughly equal to this bond angle, which should be roughly equal to this bond angle. 120 degrees add up to 360 degrees total. So when you're drawing the atoms around an alkene, you want to draw them on solid lines with roughly equal separation between each pair of bonds, the way I've shown them in this picture. You'll get a chance to practice these geometry facts in the next problem. For completeness, I will briefly mention that all solid lines is not the only possible correct way to draw trigonal planar geometry. It's just by far the most common. By the same token, two solid bonds, a wedge, and a dash is by far the most common way to draw an accurate tetrahedral atom. There are other accurate ways to draw a tetrahedral atom, but they're much less common. Please pause the video and try this problem. I hope that you actually did try this problem on paper. This problem gives us very good practice with E2 mechanism. Now let's go through the solution together. I'll start by numbering the carbons, including this carbon, and including these carbons. On the other hand, this is going to be a solvent that won't participate in the reaction, so I won't bother numbering these carbons. And I don't think I'm likely to make any mistakes with these carbons in the ring, so to save time and avoid clutter, I won't number those carbons. Now we look for ionic bonds, and we recognize that potassium is a metal. So here we have a metal-non-metal bond, an ionic bond. So the oxygen will have a negative charge in that ionic bond because it's more electronegative and pulls the electrons closer to itself. And the potassium will have the positive formal charge. Of course, there's no formal charges in this molecule, which is all covalently bonded. We can assign some roles. We start with the O-, which looks like it could be either a nucleophile or a base. We know that positive potassium is a metal, which will be a spectator that won't participate in the reaction. Neutral chlorine is a good leaving group, which means that carbon 2 is our alpha carbon. And so we see that we have a tertiary alpha carbon because carbon 2 is attached to 3 carbon chains, carbon 1, carbon 3, and carbon 5. Now we choose a mechanism using our table. A tertiary alpha carbon puts us in the bottom row of the table. And O- puts us in the right-hand column of the table. Right-hand column and bottom row means that we have an E2 mechanism. Make sure that you write that down. E2 mechanism. Did you notice that this compound is tert-butyl oxide? This compound is, again, tert-butyl oxide, but it really doesn't matter. It doesn't matter whether this is tert-butyl oxide in this situation. In this situation, tert-butyl oxide will give us an E2. but any other ordinary O- would also have given us an E2 in this situation. By the way, notice this is not tert butyl oxide, is it? Because it doesn't have an O-. This is tert butyl alcohol. And we know that alcohols are only going to participate if there's nobody more reactive around. Well, the O- in the tert butyl oxide is more reactive than the neutral oxygen in the tert butyl alcohol. So we don't expect this alcohol to participate in this reaction. It's just the solvent. Now we can continue assigning roles. We know that for an E2, we're going to use a base, not a nucleophile, and we know that O- is a strong base. So now I can label that the O- will be a strong base. Since we're going to do an E2, we know that the beta carbon will play an important role. So let's label the beta carbons. Well, carbon 1 is a beta carbon because it's attached to our alpha carbon. But carbon 5 is also a beta carbon because carbon 5 is also attached to the alpha carbon. And carbon 3 is also a beta carbon because carbon 3 is also attached to our alpha carbon. I think maybe that numbering all the carbons might help you to recognize that this is a carbon and these are also carbons. We have 3 beta carbons in this case. And notice that all of those beta carbons are attached to hydrogens. This beta carbon is attached to 1 hydrogen. This beta carbon is attached to 1 hidden hydrogen. This beta carbon obviously has 3 hidden hydrogens. So they all have hydrogens. So all of these beta carbons can participate in an E2 mechanism. So we can anticipate that there's actually going to be 3 main products. We're going to have to draw 3 separate mechanisms for the 3 main products that involve the 3 different beta carbons. I'll make a note to myself up here that we have these 3 separate beta carbons, but then down here in this picture, I'll erase this beta and this beta because I'm planning to start by focusing on beta carbon on carbon 1. So let's draw in the hydrogen on carbon 1. And we can assign a role again now. So now I'm planning to use carbon 1 as the weak acid. Remember that we've memorized that the beta carbon in an alkyl halide is a weak acid. All right, and now we're ready to draw our mechanism, I believe. So we know that we want the base to take the beta hydrogen. So here's the arrow to show the base taking the beta hydrogen. Remember that a base is an electron donor, so the electrons move away from the base towards the proton. Then we did an arrow to show the pi bond forming between the alpha and the beta carbons. Here's what the arrow looks like to show that. The arrowhead here should be pointing to the bond region, and then another arrow to show the leaving group leaving the alpha carbon. Now we can draw the product from that step. This arrow tells us to draw a new bond between the oxygen and this hydrogen. So I've drawn that the oxygen is now bonded to this hydrogen. This oxygen started negative and it lost electrons. So the oxygen changes from negative to neutral. Now this arrow tells us to break the bond between carbon 1 and the hydrogen. I already broke that bond. And to draw a new pi bond between carbon 1 and carbon 2. Here's that new pi bond between carbon 1 and carbon 2. This arrow tells us to break the bond between carbon 2 and the chlorine. So now we can draw the chlorine separately. The chlorine started neutral and gained electrons. So the chlorine ends up negative. Remember that you always change 2 charges for each mechanism step at the beginning and end of the series of electron pushing arrows. So we change the charge on the oxygen at the beginning of the series of arrows and on the chlorine at the end of the series of arrows. We don't change any charges in the middle of the series of arrows. So we don't change charges for the hydrogen, carbon 1 or carbon 2. Now, this picture is not correct yet because we haven't shown the geometry for carbon 2 correctly. Carbon 2 is an alkene carbon now in the product, and we've learned that alkene carbons should be trigonal planar, which means all bonds should be indicated by solid lines. Remember that a wedge indicates an atom that's in front of the page, and a dash indicates an atom that's behind the page. A solid line indicates atoms that are in the plane of the page. Well, in this picture, carbon 5 is in front of the page, but when carbon 2 changes to be trigonal planar, carbon 5 should change to be in the plane of the page, and so it should change to a solid line. In the starting material, carbon 2 was tetrahedral, and carbon 5 was located in front of the page. But when carbon 2 changed to an alkene, the geometry changed to trigonal planar, so carbon 5 would move from in front of the page to the plane of the page, the same plane as carbons 1 and 3. So we see that in an E2 reaction, the alpha carbon changes its geometry from tetrahedral to trigonal planar. And because of that, you might need to change how you draw a bond. You might have to change a wedge or a dash to a solid line to draw that trigonal planar geometry accurately. If you leave carbon 5 on a wedge, you'll probably lose credit for your answering. Notice that in the starting material, carbon 2 is a stereocenter, so the geometry here was drawn accurately with a wedge, a dash, and 2 solid lines. By the way, notice that carbon 3 would also be tetrahedral. Carbon 3 would also be tetrahedral, but we didn't bother to draw that geometry accurately here because carbon 3 is not a stereocenter, so we don't care much about its geometry. And the same thing actually goes for carbon 1. Carbon 1 should be tetrahedral, but we didn't bother to show its geometry accurately because carbon 1 is not a stereocenter. Remember, a stereocenter should be attached to 4 different groups, but the 2 paths around the ring count as 2 copies of the same group. So carbon 1 and carbon 3 are not stereocenters, so even though carbon 1 and carbon 3 are tetrahedral, we don't bother to draw their geometry accurately. Instead, we just simplify by drawing the bonds as solid lines, as they were given in the problem. Carbon 2 is a stereocenter, and here the geometry is drawn accurately with 2 solid lines, a wedge, and a dash. So we've drawn the product for this mechanism, or for this beta carbon. But remember that we have 2 other beta carbons that we need to deal with as well. So now we need to draw the mechanism for one of the other beta carbons. Next, I'll do the mechanism for beta carbon 3. Now I'm drawing the beta symbol on carbon 3 to indicate that that's the beta carbon I'm focusing on now. I need to draw in the hydrogen on carbon 3. And now I can label that this beta carbon will act as the weak acid here. I'll redraw this species to show that we're going to use this again as the strong base. No point copying the potassium since it's just a spectator. And now we can draw our electron pushing arrows. An arrow to show that the base takes the beta hydrogen. Here's the arrow to show that the base is donating electrons to take the beta hydrogen. An arrow to show the pi bond forming between the alpha and the beta carbons. That would be this arrow. An arrow to show the leaving group leaving the alpha carbon. That's this arrow. Now we can draw our products. This arrow tells us to form a bond between the oxygen and the hydrogen, and to change the charge on the oxygen. This arrow tells us to break the bond between carbon 3 and the hydrogen, and to form a pi bond between carbon 2 and carbon 3. Here's that new pi bond. This arrow tells us to break the bond between carbon 2 and the chlorine, and to change the charge on the chlorine from neutral to negative. Now we have to think about the geometry again here. Again, in the starting material, carbon 2 was tetrahedral because it was attached to 4 atoms. And again, in the product, carbon 2 is trigonal planar because in the product, carbon 2 is only attached to 3 atoms. So again, we have to change the geometry here. Carbon 5 should no longer be on a wedge. Now carbon 5 should be on a solid line, so it's in the same plane as carbons 1 and 3. Well, we're still not done because we've dealt with beta carbon 1 and beta carbon 3, but now we need to draw the mechanism for beta carbon 5. Here's the starting materials again, but now the beta symbol is on beta carbon 5. Now again, we have to show the beta hydrogen. Now the mechanism. The first arrow should show the base taking the beta hydrogen. Remember that the base is an electron donor, so the arrow moves away from the base, away from this negative charge, towards the beta hydrogen. Now we need to draw an electron pushing arrow to show the pi bond forming between the alpha and beta carbons. So we show that arrow like this. This is a problem where I think it's really very helpful that we keep labeling the alpha and the beta carbons. In this mechanism, the alpha and beta carbons are 2 and 5, so here's how we draw the arrow to show the pi bond forming. On the other hand, in this mechanism, the alpha and beta carbons were 2 and 3, so we used this arrow to show the pi bond forming. And in this mechanism, the alpha and beta carbons were 1 and 2, so we used this arrow to show the pi bond forming. I think it would be very easy to get confused and make a careless mistake in one of these mechanisms if you weren't careful to keep labeling and relabeling the different beta carbon that you're using in each picture. So I really encourage you to label the alpha and beta carbon that you're using for each E2 mechanism. And if you have to do multiple E2 mechanisms for the same problem, keep relabeling the new beta carbon that you're using in each picture. Otherwise, it's easy to get confused and make careless mistakes. All right, so here we're forming that pi bond between alpha and beta carbons, and then we need an arrow to show the leaving group leaving the alpha carbon. So here's our arrow for that. Now we can draw the products. This arrow tells us to form a bond between the oxygen and the hydrogen, and to change the charge on the oxygen from negative to neutral. This arrow tells us to break the bond between the hydrogen and carbon 5, and to form a new pi bond between carbon 2 and carbon 5. So I've broken the bond between 5 and the hydrogen, and I've drawn a new pi bond between carbon 5 and 2. Here's a new pi bond between carbon 5 and carbon 2. Notice how I'm trying to really go arrow by arrow and make the changes that the arrows tell me to make. That's the way to improve your skills as a beginning OChem student. Don't just take a guess as to what the product looks like, or don't just draw the product that you expect. As a beginning OChem student, try to imitate the process that I'm using. Go arrow by arrow. Remember, every single arrow tells you to erase a bond, draw a bond, or both. So look at each arrow and ask whether it asks you to erase a bond, draw a bond, or both, and then carry out those actions, and also change the two charges. Don't just draw the products that you expect. Go arrow by arrow and draw the products that the arrows tell you to draw. That's the way to improve your skills as a beginning OChem student and to get the products right more reliably. Now this arrow tells us to break the bond between carbon 2 and the chlorine. I actually already went ahead and did that in order to make room here. And it also tells us to change the charge on the chlorine from neutral to negative. Again, we see that carbon 2 began as tetrahedral in the starting material, where it was attached to 4 attached atoms. And then carbon 2 became trigonal planar in the product, where it had 3 attached atoms and no lone pairs. So again, to show that, we should no longer, carbon 5 should no longer be on a wedge. We don't usually use a wedge or a dash for a trigonal planar atom. So notice here how all the bonds in the trigonal planar carbon 2 are indicated by solid lines. In particular, we changed this wedge into a solid line to show the trigonal planar geometry for carbon 2. So we finished this problem. Let's review some helpful guidelines that we used here. The most important guideline, I think, was labeling the alpha and the beta carbons. In this picture, I labeled the alpha carbon and all the beta carbons. And then in each mechanism, I specifically labeled the beta carbon we were using for that mechanism. Here we labeled beta carbon 1, here we labeled beta carbon 3, and here we labeled beta carbon 5 because we were using different beta carbons in each mechanism. In each E2 mechanism, label the alpha carbon and the beta carbon that you're using for that mechanism to avoid confusion. Only beta carbons with hydrogens can be used for E2, but in this case, all 3 of the beta carbons had at least 1 hydrogen. Now, something I didn't mention is that you have to check whether the different beta carbons really give you different products. Sometimes two different beta carbons will both give you the same product, so you don't need to bother drawing mechanisms for them separately. But I think it's obvious that each of these products are different. I think it's obvious that these are all three different products, so it was important to draw three separate mechanisms. The reason that each of these beta carbons gave us a different product is that each of the beta carbons has different connectivity. If two beta carbons have different connectivity, they result in different E2 products. The connectivity of an atom involves the complete series of all the atoms that the atom is connected to, and all the atoms that those atoms are connected to for the entire length of the molecule. Connectivity is a technical term. Well, it should be quite easy in this case to see that each of the three beta carbons has different connectivity. Beta carbon 5 is connected to 3 hydrogens. Beta carbon 3 is connected to 1 hydrogen and 2 methyl groups. And beta carbon 1 is part of a ring and is also connected to 1 hydrogen. That's enough right there to see that each of those beta carbons has different connectivity. So we can be confident that each of those beta carbons will result in a different E2 product. And again, you can confirm that each of these alkene molecules is clearly a different molecule from the other two. What type of functional group is this starting material? It's an alkyl halide. What type of functional group is this product? It's an alkene. What type of functional group is this product? A different alkene. What type of functional group is this product? A different alkene. So each of these E2 reactions gave us a different alkene. And one thing we saw here is that the alpha and beta carbons in an alkyl halide are tetrahedral, but the alpha and beta carbons in an alkene are trigonal planar, and you might need to change the way you draw the product to show that geometry correctly. The alpha and beta carbons become trigonal planar in an alkene, so make sure you represent that correctly with solid lines. Alkene carbons are trigonal planar. Did you get this problem correct? I think this was a good workout on drawing E2 mechanisms. So hopefully that gave you some useful practice with E2. Well, we've introduced the basic ideas for the E2 mechanism. However, what we've discussed so far is not enough to get many exam problems that involve E2, correct? Because unfortunately, many exam problems that involve E2 involve further complications that we haven't had a chance to discuss yet. So we'll start talking about that in the rest of this video series. So starting in the next video in this series, we'll start talking about some further complications that are often tested on exam problems that involve E2 mechanisms. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.